Good. Let me go to the okay. I'm not sure it's good afternoon, everyone. Hopefully, you are in the similar time as mine. My name is Li Zhao. I am a research assistant professor at the University of Nebraska-Lincoln. Today, my presentation, the title is Sentiments of Rural Communities on Electric Vehicle and Electric Vehicle Charging Infrastructure. We try to find obtain insights from Twitter data. I would like to introduce my collaborators on this research. So myself is a transportation engineer and in civil engineer field. But for this study, we are looking at something like beyond my expertise. So I included a professor from social media and mass communication and another professor from community and regional planning. We got this this funding to look at for electric vehicle charging infrastructure. Right now, that's kind of a buzzword. Everyone is talking about that, and research pour into those areas in terms of technology or optimization or algorithm, where to find the location for seating. All of that and method would be using survey models, but we were thinking there are some kind of method have some limitations about we are focusing too much on technology, which is not bad, but we are more interested to look at what does the users who really use this system, what do they think, and we want to find a free platform that they can talk freely, so that we can understand their attitude toward the emerging technologies, the new energies. So that's some background and motivation why we want to do this research. And our preliminary data shows that electric vehicle and charging stations are unevenly distributed across the United States, with East and West Coast areas. There are a lot of users, and of course, they have a lot of charging stations. But in the mid-American area, including Nebraska, the users and the market and adoption rate are relatively lower. And then we think, understand those public sentiments, their attitude from users' perspective would help for those policymakers or the market or business to understand what would be the factors what are the needs from the users. So that would help them to provide the best either best locations or best services that the users actually need. Especially our focus is on rural areas, because that's by nature, it's kind of marketing stuff. The more people use electric vehicle, that's where you put charging stations. But rural areas, the adoption rate, the users market is relatively lower. So how to invoke or how to get people promote the usage in this area, I think that's kind of important to for the overall EV market. So that's the reason we focus on the rural areas. And also we try to use, as I mentioned, use social media data. Specifically, we look at Twitter data, because that platform provides a real-time and huge data that you can capture those users' perspectives across geographical locations. So they are like across Nebraska, across the United States. They share ideas, they do retweets, they agree or disagree with some comments. So we try to bring all those together to find if we can get something from that is interesting. So a quick overview about the Twitter data. Here on the top right corner, I have this this summary about number of traits that has been discussed on electric vehicle or electric vehicle, just electric vehicle. I think the keywords is electric vehicle. And then you can see that exponentially increasing. I think that aligns well with the number of electric vehicle adoption and even charging stations. It's just exploded in the past 2 or 3 or 5 years. So that means that's a hot topic. That's a hot topic that people are discussing as they, their family, their friends, or themselves. They have this electric vehicle, and they have expectations on the usage, and then maybe some challenges or needs that they are expressing during on the social media platform. So we got the Twitter data from 2015 and 2022, and they are like 27,000 tweets when we use keywords electric vehicles and rural areas. So in urban areas, this number will be way higher, but we just look at rural areas. It doesn't mean that you have to live in rural areas as long as your keywords is about rural areas. And later on, we will filter out those data that based on their geographic location. Then if you locate in rural areas, we'll filter out for further modeling, but at this moment is still all the keywords we get together are electric vehicles and rural areas. So a quick definition about the rural areas, or how does they mean a rural determination or the rural areas? There's no, based on our knowledge, there's no determination on what would be the definition of rural areas. And U.S. Census Bureau give a qualified number, which means if in this area the population is less than 5,000 people, then that's kind of a rural areas. But that's about census, and different sectors like economy or urban development or other energy. They have their own definition regarding rural. Even in our Nebraska Department of Transportation, yesterday I talked with them. They said in Nebraska we have our own definition about rural areas to account for those highway and roadways that for some administration and management purposes. So what I want to say is we just use this Census Bureau's kind of a definition to define and to find where are those rural areas. And in this data set from 2020 census, they did not give you a 0 to 1. You can define 0 to 1. 0 means no, not rural areas. 1 means yes. By using a threshold, for example, 50% of those rural census tracts. But we did not just do 0 and 1. We just look at in this area, what's the rural percentage. So for example, each county, you have multiple census tracts, and for this census tract, is that small population less than 5,000 or higher? And if it's less than 5,000, then this is a rural census tract, and then you have multiple census tract in this county, and then you will have a percentage, like 20% of those census tracts are rural area. Then this county is defined 20% of rural, and of course, a higher percentage of rural areas, a rural census tract, then this county is highly likely to represent a rural county. So in that way, so this is the map we draw that shows the distribution of the rural percentage, and we will use this as a moderator or interaction in our models. So just give you some landscape of the rural situation. And one data I want to mention that based on this definition, 63.8% of all counties, we have 3,112 counties in 48 states of the United States are classified as rural. So more than half of those rural counties based on this definition. Next thing we need to deal with is how to do topic modeling. That's a very important thing, because in Twitter data, if you use Twitter, or if you're a Twitter user, when you send a tweet, then you express that freely without any format or any constraints. We want to get thousands, tons of this message and put them into, hopefully we can get that into different topics, so that we can analyze that. This is a process we use experts from social media and mass communication. They do topic modeling a lot. And then they have the algorithm. This is a very common one, LDA algorithm, that help us to get all those Twitter data into in our study. At the very beginning, there, I think initially the first iteration, they generate 7 topics, and then we narrow down to end up with 4 topics. And the first topic is about EV charging experiences in rural areas. Second is EV driving cost, benefits, and performance in rural areas. And topic 3 is about the infrastructure investment in rural areas. And the last one is the policy, the equity, including energy, economic, and environmental on those charging infrastructures. So those topics are like a broad coverage on electric vehicles and electric vehicle charging stations, because that's charging infrastructure also one of the topics that EV users are concerning, especially at the beginning of this stage. This years we are still kind of a lack of the infrastructure for some areas. So that's 4 topics, and then for each tweets we have a sentiment. Sentiment means either this topic shows a positive attitude, or a neutral, means there's no positive or negative sentiment showing up based on the algorithm we use for sentiment analysis. So we could be able to category each tweets into one of those 4 topics, and also for each tweets we have a negative or neutral positive sentiment associated with that. So I will go a little bit quicker because later on are just models. So for the Twitter data, we filter out those missing. We have those tweets, the age and gender, because some people do not have age, gender filled in. And if you report you are 25 years and as a female, then we will take it as the data we have. But if it's missing, we just filter out. We also filter out those people like no information regarding their geolocations and their rural areas. And then finally, we have over 10,000 data that we used into the model. So this is the overall data. I guess I mentioned that most of those. So let me just mention it again. So about sentiment, that's the dependent variable. And tweet topics, we have 4 topics, as I mentioned, and we have tweet senders, sex, and their gender, that's binary variable, and the age, from 13 to 79 years old, and number of electric vehicle charging stations at a certain location, number of electric vehicle accidents in a county level, and the rural indicator, whether this area is rural, yes or no. And I think later on in our third model, we use as I mentioned, a percentage rather than yes or no. But at the very beginning, we just want to screen out if this variable is significant or not. So number of station, number of accident, I want to speak a few words more. So our hypothesis is that the more EV charging stations you have in your county or in your community, then the higher sensitive or the more positive sentiment you want to have. Then the number of accidents that's on the country, the more electric vehicle involved accidents you have in nearby you, or even your friends or your family have those accidents involved, then the more the sentiment is toward to more likely a negative. So we want to look at if those relationship holds and our hypothesis values. For the first model, we just threw everything, all those variables into this generalized linear regression model. Just look at how sensitive of those variables to this dependent variable, which is the sentiment of each trait that we are interested in. And it shows that so number of charging stations and number of accidents is something like what our hypothesis align with our hypothesis. So the more charging station you have, because this is a positive coefficient and accident is a negative coefficient. Rural does not show this is not significant, but when you look at rural as a moderator, the interaction term, then the rural the coefficients is kind of exaggerated. Means in rural areas, number of charging stations, the more you have, then the even more positive sentiment you have. Similar for accidents in rural areas, the charging, the crash you have, the more you have, then even more negative sentiment you will feel through their trace data. So that's like very general idea from this this linear regression model. And then we are thinking, because of the nature of this data, the data has hierarchical structures because there are many information we talk about in county level, and then for each trader, it's like individual level. So we try to mix this data into a hierarchical model, and to account for those either within variabilities and also among group variabilities. So the result is I would say it improves a little bit if you look at the AIC, and also the significance for those number of stations and accidents still there, and rural still the same, and other variables have a little bit better performance, but we cannot tell at this moment. At this moment, my hypothesis for number of charging stations and number of accidents still holds. And also for the topics, we will see that all those topics are significantly compared to topic 1, which is the EV user experiences, and then topic 2, topic 3, topic 4. I can't remember. I think you probably did not remember. I can't remember that either. But those other 3 topics has a positive, like more positive sentiment toward the first one. I will have this in the conclusion part later on. And then last model, we are thinking, because we are talking about the geographic locations, and then the hierarchical model also have a little bit factor. You can feel that they try to hierarchical those people within the county. So we just set it free. So for all those people in the United States, we have their coordinates for their traders, and put that into this GWR model, and to see if we can find something new in terms of their spatial distribution. And now we have for this GWR model, you do not have a p-value, but we used other method, just listed those red coefficients. Those are significant. And similarly, as we found from compared with model 2, but this time male has like more positive attitude toward to the charging electric vehicle than female, something like that, but others keep the same. The model is performed a little bit better. For the interest of time, I will just go to the conclusion. So we think trader data is a good data source that we can ask for help to understand the driver, the EV users, because if you do survey, it takes time and cost money. But for Twitter, it's free, and we have a large data set. And we think structure model is a good way to look at either spatial or you can use a structure for your data purposes. And the sentiment influencing factors, I probably won't go through everything, but at least 5 of those factors are significant. And people are talking most like electric vehicle cost benefit and infrastructure environments. That's the people we are concerning the most in rural areas. So if number of accidents, as I mentioned, it would be a negative sentiment if you associate with electric vehicle accidents. And then males are more optimistic about EV usage, and the age does not really show significant difference in sentiment. So we want the most important thing, a conclusion we had would be counties with higher rural percentage expect more positive sentiment toward electric vehicles, which means that rural areas, they are more expecting or more have a higher expectation on this electric vehicle. That's a very big potential market that worth investment. Okay, there's some limitations.
Yeah.
I guess
okay, yeah,
I have to stop here.
Yeah, any quick question from the audience? Maybe just 1 minute Q&A. Oh yeah, I just have a very quick question. So for like at the beginning when you filter all the Twitters, have you considering adding charging stations in there, because it could be also related in addition to EVs or Tesla or rural, or because some terminology related to EVs that are also related.
Yes, so we saw so these keywords when we think about charging station, and we assume that if you talk about charging station, you probably have some electric vehicle associated with it, but that's a good point. We did not specifically mention about charging station. At the very beginning, we'll just look at our idea, our design was look at rural electric vehicle usage. And then later on, we found that a lot of people, for those EV users, they are interested in charging stations.
Okay. Yeah. Just
Thank
a
you.
suggestion. Yeah, adding that would be helpful. Yeah, to get more data.
Yeah, right.
Yeah. Thank you.
Thank you.
Yeah, and let's move to the second presentation. So there is a little bit change in the schedule. So now we are swapping the order between Kentaro and Bala. So Bala will be the next to present his work. It will be what happens when SAV fleets compete and a fare-based analysis. And just a second reminder that we will have the presentation for 20 minutes each, including the Q&A.
Do you able to see my slides?
Yes.
Yeah, okay. Thank you. Thank you, Antal. So this is Bala. Today I'm going to present about what happens when SAV fleets complete a fare-based analysis. This is the work I did with Doctors Krishnamurthy Kurumurthy from ANL and Dr. Kara Kakalman. Until recently, I was postdoc with Dr. Kara Kakalman at UT Austin. So basically, the idea behind this work is for example, in a traditional TNCs, there are 3 key players: the passengers who request rides, drivers who offer rides, and the fleet managers who are matching the passengers with the drivers. Whereas when we consider the SAVs, the driver is taken out of the equation. There are only 2 players, passengers and the fleet owners. The objective of both the passengers and the fleet owners is to maximize the profit, that is benefit minus cost. So generally customers choose the rides. If they want to travel from point A to point B, they choose the rides based on fare, weight, date differences. For example, service quality and past experiences. Like some customers tend to choose option X or option Y based on the past good or bad experiences. So that also they will take into account. So in this study, we simulate a competition between two fleet owners in Polaris, which is an agent-based simulation model using fare and fleet size assumptions. So the how this thing works is like there are two owners, like owner one and owner two, and then we are offering we are trying two strategies like the price based strategies. One is time of day pricing, another is zone based search pricing, and then both have a certain fleet sizes, and then both has only one vehicle option, that is standard 4-seater option, and then we are testing the option with dynamic ride sharing and then the individual rights for both the owners. So there are some few assumptions we are considering here. Some of it is like all the things we are considering only standard SAVs, and then the vehicles are assigned on the first come first serve basis. There are no reservations allowed, and then we are considering the loyalty of 20% to each owner. So due to their past good experience with certain owners, so like 20% of the customers tend to choose always the owner one, irrespective of the ride offered by the owner two. Likewise, our owner two, there are 20% loyal customers, and then the rest 60% choose ride based on the lowest fare. How this work is, for example, I will have, for example, both Uber and Lyft in my mobile phone. And if I want to travel from point A to point B, I'll just check which is the lowest fare and choose the ride based on the lower fare. Whereas the loyal customers will choose their respective owners, always a single respective owners. And then there is a 40% discount offered to the people who use a DRS, that is dynamic ride sharing. If the customers willing to share ride with other owners, they will be offer a 40% discount. And then here 3 fare strategies are tested. Actually 2 fare strategies, like time of day pricing and the zone based search pricing. Third one is the combination of the both. And then for the zone based, the time of day search pricing works depends, like there is a peak, there is a high price charge during certain hours of the day, whereas the zone based search pricing is according to the search multipliers. Like if the, for example, the region is divided into zones, if the demand in the zone is more than the supply, then the zone based search pricing is activated, like more fares will be charged. So these are some of the key notations we are using in our mathematical model. So as per the time of day fare strategy here, like 1.5x more fare is charged during the morning peak hours, that is from 6 to 9 a.m. in the morning, and then from evening evening 4 to 8. So these are fixed, the time, the peak hour is decided in advance, like 3 hours in the morning and 3 hours in the evening. And during those time, in the time of day fare strategy, 1.5x fare, a higher fare is used. And then in the zone based search strategy, in the, for example, in the zone, if the demand exceeds the supply, then the 5 times the fare is charged. That is, the fare at the time is multiplied by 5 times. And then in the combination strategy, we are using, for example, during the peak hour, if the demand exceeds the supply, then we implement both the TOD and the combination of TOD and the GSP fare strategies. So here we are testing the 10 different scenarios as shown in the table for the Austin, Texas region. So the Austin, the map is shown in the left-hand side. So the Austin region, there are 1.8 million residences across 5,300 square miles. And then the region is divided into 21680 TAZs and 16,100 links. And then for all the scenarios, we assume 10,000 SAVs for owner one, and for 10,000 and 5,000 SAVs for owner two. That amounts to roughly 1 ACV per 180 residents in scenario in owner one for owner one, and 1 SAV per 360 residents for owner two. And then we charge a mini pickup fee of $1 for the ride, and then 0.5 $0.5 per mile for each mile they travel, and 0.25 for the each minute they are in the line, they are in the vehicle. And then the fleet owner cost pays, for example, for vehicle maintenance, the fleet owner cost is about $50 per day, and then $30 per mile. So if there is a more empty vehicle miles traveled, like the owner needs to pay $0.30 per mile the vehicle is traveling empty. And then in the scenarios, for example, here there is an assumption that both the owners does not know what the fare strategy is implemented by the other owner. So in the initial 4 strategies, we have tested what if both the owners have a similar fare strategies, and then from scenarios 5 to 10, both owners try different fare strategies, and we have tested how the different parameters like on how the different parameters like average peak hour, wait time, idle time, and then EVMT and profit changes from owner 1 and owner 2. So this is the baseline fleet performance indicators. As you can observe from this table, the peak hour wait time is higher. For example, in scenario 5, when owner 1 implements a flat fare strategy and owner 2 implements a ZSP strategy. So this is understandable. When owner 2 have a ZSP strategy, the fare is going to be higher. So the 60% of the customers who choose the cheapest fare tend to focus more towards owner 1, and there is more waiting time. And this also you can see from the scenario 10, like when owner 2 has a ZSP plus TOD strategy, so even higher fares, and owner 1 with TOD strategy has a higher peak hour wait time. And then if you consider the median fare for the rides, which is highest when the ZSP plus TOD strategies is implemented by the owner, and then the average idle time is highest when the ZSP plus TOD strategy is implemented together, and then the profit is highest when as expected when ZSP plus TOD is together implemented. And then these are some of the what is the effect of we'll just look into what is the effect of these different fare strategies on wait times and average vehicle occupancy in this slide. So with flat fares, owner 2 has longer peak hour wait times than owner 1. So when both owners adopt same pricing strategy, a small fleet owner offer short wait times. The reason could be the customer demand patterns and optimal vehicle deployment. So when different pricing strategies implemented by the owner, the average peak hour wait time is higher for a higher average peak hour pickup time is higher for owner who offers cheaper fares. This is acceptable. This is understandable, as 60% of the riders choose which is the option based on the cheapest fare. And then the figure at the top shows the average vehicle occupancy. The x-axis shows the 10 scenarios, and the y-axis shows the revenue trip AVO of the for the 10 scenarios. So as we can observe that in the on the extreme left, the first one, when the flat fare is implemented for both owners, the AVO of owner 2 is higher compared to owner 1. So as here also with different fare strategies, AVO is higher for owner with cheaper fare. So as if the fare is cheaper, so that has a huge impact on both the wait times and the AVOs. And then next in this slide, we look into what is the effect of these different pricing strategies on the owner's revenue. The figure at the top shows the median fares per passenger rides in all the 10 scenarios. The figure at the bottom shows the profit. So when both the owners implement flat fares, owners to profit is at least 25% more compared to owner 1. This is due to the larger operating cost, because owner 1 has close to 10,000, around 10,000 vehicles, and owner 2 has only 5,000 vehicles. And then when both owners use ZSP or ZSP plus TOD, so the owner 2 sees higher medians and profits. Once again, like the cost of 1 or 2 in maintaining the vehicles is less. Also, when ZSP plus TOD is used, as you can see in the fourth bars here, like the compared to the flat fare strategy, the profit is increased to 8-fold and 10-fold for the owner 1 and 2. Always when time of day pricing strategies used with respect to the flat fares, so time of day, there is a minimum of 6% of increase in revenue for using the time of day fares compared to the flat fare strategy. So in this slide, we look into the effect of pricing strategies on the empty vehicle miles traveled and the vehicle miles traveled. The figure on the right shows the percentage change in empty vehicle miles traveled with flat fares as the base for owner and owner 2. So we are considering here, like for owner and owner 2, if there is a flat fare, compared to that, if we have a different fare strategies, how much the EVMT has changed for the owner 1 and owner 2. So as we can see, when both owners employ ZSP or ZSP plus TOD, compared to flat fares, EVMT decreases by about 6% for owner 1 and increases by 2% for owner 2. So like the highest increase, as you can see in the figure, like in the when owner 1 have TOD and owner 2 has ZSP plus TOD compared to the flat fares. So when we look onto the vehicle miles travel as shown in the figure left, here also the percentage change in VMT is shown with flat fares as the base. When both the owners adopt the same pricing strategy, their VMT consistently shows a decrease compared to flat fares when owner 1 implements ZSP and combined with TOD. So to conclude, on an average across all scenarios, the vehicles runs for 11 to 12 hours per day. That is a quite number of time, like more than 8 hours of working hours. So with same pricing strategy for both owners, smaller fleet provides shorter wait times, higher vehicle occupancies, and decreased vehicle miles traveled. Further, implementing time of day profits, regardless of other owners' strategy, consistently boosts the profits of the implementing owner by 30% to 90%. TOD pricing is always beneficial. Further, when DRS is used like with similar pricing strategies between owners, there we can experience higher AVOs due to the preference for cheaper fares, because people want to go from the destination from their home point to the destination with a cheaper fares. EVMT is highest when ZSP plus TOD is used by one owner with cheaper alternative by the other owner. This is also understandable, like when we are looking for cheaper fares, like the vehicle needs to go from one part to other part when they have a ZSP, so that increases the empty vehicle miles travel. However, though the ZSP strategy boosts the profits, there is a limit for how much the prices or the fares can be increased. If we keep on increasing, like that deters the riders from taking the rates. That also one of the things we need to look in implementing the fare-based strategies to the customers. Thank you very much.
Oh, thanks for the presentation, Bala.
Thank you.
Any questions from the audience? Yeah, and also feel free to unmute yourself and talk to ask the questions. I think we have 1 or 2 questions. Time allows for that. Okay, yeah, I think maybe I can start with the questions. I think my first question is, like, did you look at the geofence for the services at different area, or they are like both operate on the whole 6 county region of Austin?
Actually, in this study, I did not look into the geofence. The study looked into the entire 6 county region of the Austin. However, as a trial run initially for testing phase, I tried this thing for the smaller Bloomington region. So there the EVMT is like, since it's a shorter region, EVMT is less, although the trip distance is less. Yeah. But with Austin region, I have tried only with the entire 6-county region.
Okay, okay. Yeah, I'm asking this because it could like possible that they operate on different regions and that could have an impact on the results. Yeah. And yeah, and also I think maybe I missed that, but so in order to determine the like because now we have two operators and the writers can kind of choose between them. So what is like the way of determining like which operator to choose? Is it always the lowest fair like to match them, or basically what's the like the matching criteria?
Yeah, each operator has 20% loyal customers, that is assumed. Like operator 1 has 20% loyal customers, owner 2 has 20% loyal customers, rest 60% choose the rate only based on the lowest fare. That's what this study included.
Okay, okay.
Yeah. So this is like just how we go. Like if we have a mobile phone, if we have Uber and Lyft, take which is offering cheaper rate, just pick that option and go. So that's how it's designed.
Yeah, that makes sense. Yeah. Thanks. Any other questions from the audience? No? Okay. Yeah, thanks for that. I think we can move to the next presentation. So the next presentation is from Gabriel Nova, called a Bayesian data augmentation approach for attribute attention sequences in the RUM-DFT model. I think is not here to present, but there is a recording of that. Amit, can you pull that up to play the video?
Hello everyone, thank you for coming to see my presentation. My name is Gabriel Nova. I am a PhD candidate at TU Delft, and this work was made with Angelo Guevara and Andrés Musalem from Universidad de Chile. And today I'm going to present a Bayesian data augmentation approach for attribute attention sequence in the RUM-DFT model. The later results are preliminary, but it's still promising what we can learn from this work. In general, the choice process is defined as a series of steps that people or decision makers take to choose an alternative. For instance, Engel et al. 1968 from the area of psychology defined 5 cognitive states related to the choice process. First, the decision maker must recognize that is in the choice situation, and then he or she must perform an information search process in which, by recalling memory and previous experience, the decision maker can update their preference or utility, but also this person can look at external information, algorithm, and update his or her utility or preference. And then the decision maker evaluates the alternative with some decision rule and make a choice. After this experience, there is a stage of learning in which the decision maker incorporates this learning process for future in similar contexts. So in the previous work, in the same line, we include the information search process in which how the people look at the information and how they process in their deliberation process within the canonical representation of the random utility maximization model, following a decision field theory assumption. So I will join this assumption and then explain the RUM-DFT model, and then which is the innovative approach that we are presenting in this work. From psychology and cognitive literature, we found two main different ways to represent the information search process and deliberation process that occur before the people make a choice. On the one hand, the random utility maximization model assumes implicitly that decision makers make an information search process in depth. That means before to take a decision, decision maker compute the utility based on the all attribute and coefficient from the same alternative. But on the other hand, there are other models like decision field theory, in which this model assumes that explicitly that in each timestamp previous to the making a choice, the decision maker look at the attribute values across alternative and update the preference or utility, and then look at the next attribute. So in this model is a dynamic model in which in each time step the utility value or preference are updated according to the attribute I'm looking at. So the idea is to use the DFT model assumption and we incorporate them in the previous work, and we presented the random utility model combining to DFT assumption. So in general, decision file theory assume dynamic preference which are updating across the deliberation process, and each time step decision maker look at one attribute, a specific attribute, and update the preference until he or she make a decision. So Thomas Hancock and colleagues show in different work that decision field theory capture the cognitive effort that people are making through the different election, and also showed that this model fits better than conventional model. However, the economic interpretability of the parameter of decision field theory are not so clear, and the idea is to use the assumption behind decision field theory within the random utility maximization, and in all previous work we construct this model in which we consider dynamic utility, and each time during the deliberation process we are assuming that people look at a specific attribute and update the value of the utility across the different time steps until he or she make a decision. This allows to estimate the coefficient of the attribute, but also to those one related to the deliberation process. So following this approach, here in this figure display the information search process for two attributes in the choice situation, but also the right displayed for three attributes. And we can see that people are looking for at different attributes to update the utility. On the left, we consider only the travel time and travel cost, and this decision maker decide to choose bus at the timestamp 5. On the other hand, on the right, we include waiting time to analyze how was the complexity of the deliberation process, and based on the same individual, he looked at different attribute but still decided to choose bus. So we call this sequence of attribute attendant as HN, and we are gonna use this concept to make more clear the representation afterwards. So in general, the RUM-DFT model at each timestamp the decision make to decide within choose with the current information or in the next timestamps to look for a new information and process the attribute values and make a decision. And this iterative process is done until he make a decision. So here I'm representing the mathematical formulation. We're considering the probability of choosing at time t when the expected value of the current utility and the future utility, and not change more than the threshold modeled with the delta parameter, and the opposite is the probability of searching for information. And then if the people decide to choose a time step t, the decision-making choice the highest utility following a logic approach. And in the other hand, if the people decide to look for information, he needs to decide which attribute to look at the next time step. So here in the bottom we can see how the utility is composed across the time step. We have the memory parameter represented by alpha, and we use the previous utility value and update it with the beta coefficient and the attribute value at time step t. So, well, after the iteration, here I'm displaying the local likelihood function, considering that we know the specific sequence of attended attributes for each decision maker, and in the initial work we also derived the local likelihood function when we only know the iteration time, or what was the number of attributes that people attended, and also when we don't know this information. But we're focusing in this case with a specific sequence of attended attribute, and with that we can say that we can replicate the dynamic behavior utility during the liberation process, but also we can recover the parameter related to the choice process, and also related to the liberation process we can know what was the memory factor and the tolerance the decision maker have. And in this case, when we know the actual sequence of attended attribute, the parameter of the model correspond to the marginal indirect utility in conventional random utility maximization model. So this is crucial to know this sequence, because when we don't know this sequence, we not can recover this last property, but also it's more difficult to compute the local likelihood when we consider more attributes. So in this work, we are gonna use the Bayesian approach in order to compute the values, but considering a candidate of different sequence of attributes. So we are starting with the Bayesian augmentation approach, the traditional one, and here in the first formula we have the unconditional probability, which depends of the parameter of the model, but also depends of the integral of the all feasible sequence of attended attribute, which make difficult to compute, as discussed before. So we can use the posterior distribution, which is proportional to the local likelihood function of the prior. We can use the distribution of the sequence of attributes and betas and compute that, but extracting value directly from this formula will be extremely computationally slow, because at each iteration the integral over all possible path or sequence that the decision maker may can follow need to compute it. However, we can fix this sequence, and the process of drawing random values become more efficient following the give sampling process over the parameter, over the model parameter. So the idea here, we are fixing at each decision maker level the sequence of attribute, and we are proposing candidate for the parameter value, and in the next time step we are proposing a new candidate for the sequence of attribute from the distribution. So So in this case, I'm displaying the pseudocode of the Bayesian Augmentation process for generating a candidate for the model parameters, but also for the sequence of attended attribute. And in the step 0, we need to start with initial value for this parameter of the model with a prior distribution with a mean, but with extremely large value for the variance. And also we're computing the initial value of the sequence of attended attribute for each decision maker. So then across each iteration, using the current value of the parameter, we propose a candidate parameter of the model, beta tilde, from the we draw from the random distribution considering a mean and large variance, and then we compute the probability of acceptance, and we compare to a random value in order to know if the local likelihood if improved or not, in order to accept this new set of candidate parameter. If doesn't happen, that we using the same as the previous, the same beta value as the previous one. And then considering fits in this set of candidate parameter, we propose a sequence of attended attribute for each decision maker, and here we are changing the order randomly from the sequence of attribute, and then we calculate this new probability of acceptance, in which we are only changing the we are comparing the previous attribute sequence at individual level with the new one. So this is a vector for all the decision maker in the simulated database, and we generate a uniform value for all of them, and we accept at each decision maker level if this sequence of attended attributes improve or not the local likelihood. So this is the overall pseudocode. So now I'm gonna present different results, and the first one is to display how we simulated the information search process and choices. For that, we're following the RUM-DFT approach with 4,000 individuals with 4 alternatives and 2 attributes, travel time and cost. And following this approach, people take different time steps to make a decision. On average was 5, and we found in the database that the maximum duration time was 10 time step. So following this approach, we estimated the model, but consider maximum likelihood estimation approach in order to know that if the model requires the parameter. We are displaying here that the initial preconceived utility and the parameter associated to the coefficient of travel time and travel cost are quite similar, but also we found that the attention weight for the travel cost and the memory factor are also recovered, as we can see this test against to the true values. So now the next step is to apply the Bayesian approach, but here we're considering that we know the actual sequence of attended attribute in order to know if this approach can obtain this convergence distribution of the parameter within a range to the true values. So we can see that after a few iterations of the parameter converts to the true value. For instance, BT time was -2, and this is I think in 100 iteration the model, this approach can stabilize the value. And also here the histogram display the latest iteration. So this analysis show that this approach are converting to the true value. But the more interesting thing was to when we're considering the Bayesian augmentation, when we don't know the actual sequence of attributes, and we are inputting this beta parameter, but also the sequence of attribute at individual level, and take more longer time to adapt the role who measure the acceptance rate. So we increase the number of iteration for the born values, and so we're now only considering from 10,000 iteration to 2,000 iteration, and we see that the this algorithm provide that betas can converge through the true value. Is more clear to the coefficient associated to the attribute, but is not so clear for the iteration process coefficient. So we are still working how to input this, or how to draw the sequence of attribute value considering with a more weighted approach, in order to not repeat the other that we already compute, in order to increase this process. So the main conclusion in this ongoing research was moving from traditional estimation process to apply the RUM-DFT model and estimate this model using a Bayesian approach. First of all, the estimation process is considerably less complex, and when we know the sequence of attribute, we show that the coefficient parameter and the iteration process coefficient converts to the true value, and due the lack of time I didn't display here, but we also try to estimate, to generate a random distribution for the parameter, and this model considering this approach recover the true value as well. On the other hand, when we are annotating the sequence of attended attribute, this is a preliminary result, but are displaying that the attribute coefficient and the iteration process coefficient convert to the true value in a long time, because we are generating draw from the beta values, but also the sequence at individual level. So we need to more iteration to convert to that the distribution convert to the true value. The more interesting thing that I didn't show here, that when we are looking at the matrix of the sequence of attended attribute at the population level, and we calculate the attention weight for the travel cost and travel time, we obtain the probability of attendance with the true value. So this is important. We are not stating that we are recording the actual sequence of attribute value. We need to work on that, but we are seeing that here in average we are recording the attention weight on the entire population. Thank you very much.
Okay. Yeah. Thanks, Ahmed, for playing the video. Yeah, I don't think we have like Q&A for this, and we are also running out of time for the schedule. Let's just yeah, it's almost half, but we have a couple minutes over. Yeah, let's jump to the next one. It's from Max Leno, and the topic is revealing shifts in the valuation of schedule delay during external disruptions and application of departure time choice models using smart card data. Please go ahead.
Okay. Can you hear me?
Yes, we
Fantastic.
hear you.
Fantastic. Thank you very much. Hi, everyone. My name is Maximiliano Lizana. I am a PhD student at the Institute of Transport Studies at the University of Leeds. And this presentation is about the estimation of the pattern time choice model using smart card data, try to overcoming some of the limitations that have at the moment restrict the use of this passive data to estimate this kind of model. And one particular application to disruptive episode occurred during the COVID-19 pandemic to observe some elements that this kind of model can tell us about change in public transport user change. So to study preference in of traveler to start the trip at a specific time of the day, the path to time choice model has been traditionally implemented in the literature. In this kind of framework, public transport users try to optimize the decision about when to travel, considering a different set of factors. For example, travel time, could be fare, crowding levels, and one particular variable that is called also a schedule delay that is a little bit tricky to understand. So I'm going to try to explain it in the next slide. So consider, for example, that someone need to arrive at 9 a.m. at work. So we can ask what time this person would prefer to arrive. So it is highly probable that this person will try to arrive a few minutes before 9 a.m. So as this picture illustrate, this person will experience a highest utility or the lowest disutility closer to this particular time. So we call this the preferred arrival time of that particular traveler. Of course, if this person arrived quite earlier or quite late, this dissatisfaction that this person will experience will increase. So this person is rational. So we try to use that theory to explain this behavior. So if we change the point of view from a preferred arrival time to a preferred departure time, we can do something related to when travelers decide to travel. So we can do that by subtracting to the preferred arrival time the travel time and the condition of non-congested network. So in that way, we can get the preferred departure time that follow the same characteristic of optimization that I explained before. So in a condition, in an optimal condition, each traveler, the actual travel of a person will be the same, will occur at the same time that they prefer departure time, right? But in reality, that's not true. And why not? Why people could start their trip at a different time of the preferred departure time? So I can explain this, or not I, well, it is explained. The answer to this question is illustrated here. So let's think that the preferred departure time of a person is at 8 a.m., for example, in the morning. So what usually happens in network, particularly in public transport and also well, in car commuting, is that many people share the same preferred departure time. So if travelers share the same preferred departure time, what they observe in reality is that at the moment of their preferred departure time, they observe also the highest travel time in the network. So people can decide to shift the actual trip at a different one. They can decide travel earlier than the preferred departure time, and that is called schedule delay earliness. So that's the difference between the preferred departure time in the morning, whatever the period that you can analyze, and the actual departure time. Also, could be the same if it's later. So what is happening here? Here, a traveler is deciding to shift their preferred departure time, traveling earlier, but what they are gaining with that? They are gaining reducing the travel time. So by moving their the actual travel from the preferred departure time, they get a reduce in the travel time. So I am interested in understand this kind of trade-off using a random utility framework, particularly with smart card data on bus users. So there is a very old framework that is still quite useful to model this behavior. So in this approach that is proposed by Small in 1984, the observed utility to start a trip at a time interval S for a person end depend if there is a flat fare, for example, we can use or consider at least two variables here that could be travel time, that also depend of the moment that the person decides to travel, and the schedule delay, this shift that I explained before. So the issue with this approach is that to estimate the schedule delay earliness or lateness, that is a dummy, could be early or late, we need to know the preferred departure time. So in the literature, this preferred departure time is usually observed only in state preferences and is not observed in traditional revealed data. I'm talking about traditional travel household survey or passive data such as smart card data. So there is some element that is missing here to estimate or to use smart card data in this approach. However, there is some strength here in this method, that is the estimation of the trade-off between this travel time and a schedule delay that can be obtained as a ratio of the partial derivative of the observed utility respect schedule delay and travel time. And this particular evaluation is quite important because how much time, so it's just a trade-off between the is to, well, there's still few of them that estimate this kind of model, but mostly related to car commuting. So there is a lot of room for the estimation of this model, for particularly for the analysis of traveling time preference among public transport users. Additionally, this kind of model has not been implemented, particularly on disruptive events. For example, I'm talking about the COVID-19 pandemic, could be social protest, and see how this trade-off between travel time and schedule delay differ from a baseline and so on. Some, in general, well, most of the gap I already told up, so I'm going to skip it. So I'm going to, in this presentation, we try to answer two research questions. If first of all, if we can use smart card data to estimate these kind of models, and particularly if we can observe shift in the evaluation of a schedule delay respecting travel time, considering some assumptions. So we saw this a case study, the public transport system of Santiago, Chile's capital. Santiago has a population of around 7 million inhabitants, and during the before the pandemic, around 20 million public transport trips per week were registered by a smart card data system that is available in Santiago. So this smart card allow the but in each transaction to record the ID card, the timestamp, mode, boarding and station, and so on. So we can observe the moment that every public transport user board a bus and estimate the travel time using the automatic vehicle location of buses. So for we focus the analysis trying to estimate the model at different episodes to observe if there is a coherence result in terms of the evaluation and the preferred departure time that is missing. So we check the ridership data from 2019 to 2024, observing different kinds of episodes that are potentially relevant to observe differences in this regard. So we consider at the end 5 different episodes. We started with the baseline, where the first model is specified, and then we have another period that is after. Sorry, this is the amount of transaction in the system. In blue are the buses, and in green are the metro transactions. So we see here that after the social unrest happened in October 2019, there was a important drop in ridership levels, and then occur the pandemic. We have the lockdown here. So we have a period that we consider the after lockdown, or still a period highly affected by the pandemic mobility restriction. And then we consider also post-pandemic one in early 2022, and then post-pandemic two in early 2024. So what we expect to find in this here, we expect to see differences in the trade-off between travel time and schedule delay, and also observe difference in the preferred departure time that, as I said, is missing. So what we need to observe the preferred departure time. So we made a modification to the equation proposed by Small in 1984, as I mentioned before, by considering that the preferred departure time in our model is a latent variable in terms of that we cannot observe it directly. So we consider that the preferred departure time of one particular individual is a random variable that follows some particular distribution, which parameter can be estimated within a mixed logic model. That was the approach that we expected. So at the end, we can simulate in the model, considering the people decision in terms of when to travel, and see how this density function change between episode, and with that we can estimate the betas, and with the betas we can observe also change in the evaluation of the travel time respect schedule delay. So we apply this model considering particularly the morning rush hour, where schedule delay is more relevant. So we consider for the 5 episodes 20 different time interval of 15 minutes between 6 a.m. and 11 a.m. We consider for each episode also 10,000 unique random IDs that were randomly selected for the whole population, if we can say it, in each period, and the Johnson distribution, because it was the option that offered us more flexibility in terms of the shape of the distribution. So first of all, we were able to estimate betas with expected sign, both negative. So if travel time increase, of course, this utility will increase. If the schedule delay increase, also is negative. That means if someone is someone is traveling at the increasing the distance for the actual travel respect to the preferred departure time, that means that this utility also increase, and both are statistically significant. That's of course something that we were trying to find. Also, the parameters of the distribution were statistically significant, which allow us to say that the specification that we are proposing is able to capture the heterogeneity in terms of the preference of departure time in our sample. So we try to validate our models, comparing the valuation of travel time valuation of schedule delay with existing values in the literature. So at the end, we obtained that public transport users were willing to reduce, were willing to they were seeking to save 1.41 minutes of travel time if they increase in 1 minute time of schedule delay. That was a trade-off what we found, and that is exactly in the middle range of the observed existing literature. What allowed us to continue to estimate this is calibrated in the baseline for the other episode that I showed you before. So with the validation already okay, and now I am going to show you the difference in the density function that we observe, and also in the valuation of schedule delay and travel time. So these are the results for the latent density function of the preferred departure time for each of the period. Just for simplicity, I want to suggest that you focus in this, that is in the baseline. Here you see that the peak occur at 8 a.m. in the morning, where this indicates that there is the highest probability to get a preferred departure time of one person was around 8 a.m. If you observe the change during the pandemic, the model indicate that there was a complete shift compared with the original shape of the density function. So it seemed that first of all, there are a lot of chances to observe people with preferred departure time quite early in the morning, between 6 and 7 a.m. And that is according to what we expected, because in this scenario, if we remember during the pandemic, people were trying to avoid crowding, for example, that occurred at the a.m. in the morning. So it was okay result. And additionally, we observed that this was only a circumstantial result, because after the main restriction were removed, the density function started to come back to the original shape. However, we observed still a shift a little bit earlier than before. That means that still there was, at least after 3 years, still a long-lasting effect in the preferred departure time of public transport users. So in terms of the evaluation of schedule delay respecting to travel time, we observed that during the pandemic, the passenger experienced a relative increase in the evaluation of schedule delay respecting to travel time. What does mean? As I said before, schedule delay is just the difference between the actual moment of traveling compared with the preferred departure time. So in the highest valuation means that if someone was willing to change or to shift 1 minute of departure time, travelers were trying to seek more travel time for the same behavior than the baseline. So at the end, they were trying to keep as closer, as near to the preferred departure time as possible. Of course, that means that they were not willing to change their mind in terms of when they want to travel. And that is related to the density function that we showed before. So if the peak here was at this moment, people were not willing to travel after that. We try to keep as closer to the preferred departure time for the condition that we see. And then we observe also that also it's expected that the values start to coming back to the original ones. So as a main conclusion, we present here as is for the best of our knowledge is the best is not the best, is the first application of smart card data to estimate the departure time choice model. We try to outcoming some gaps that we found in terms of methodological approach. And our next step is to try to include more variables in our models. For example, crowding, for example, reliability in terms of travel time, that could also be relevant. And in this approach could be also be applied to estimate value of travel time when fare is different in time episode. That is not the case for our particular study case. That's the themes of the author, and thank you very much.
Cool. Thank you. This is a very interesting topic. Yeah, it's like also like it's Olympic right now. I wonder like what people in Paris are traveling. So this could be very helpful if we have the data for this. Yeah, I think for the sake of time, I just have a very quick question. Have you compared, like, I know that, so from what I can see, it's in the morning peak, right? Have you compared anything like for the morning peak versus afternoon peak? Do you have that like data for that? Is there any difference?
Well, I have the data, but I'm not look at that particular in the afternoon. The issue with the afternoon is that when someone finish the job, they take whichever is the first bus, right? They don't wait depending on it is the for example, they are not stay in their job just to wait until the off peak, for example. So what happened in the afternoon is that the schedule delay at least is not statistically significant because people just want to get home as soon as possible. So there are evidence in the literature that the schedule delay at least is not relevant in the afternoon peak. But yeah, of course, we should try to do that. But yeah, I think that is something very, very interesting also to consider. Thank you very much for the question.
Yeah. I feel that like in the afternoon, like the penalty is like more lower before. I mean, also after because it's not like a commuting like constraint in the morning. Cool.
Yeah.
Cool. Thanks.
Thank you very much.
Yeah. Let's move to the next. The next presentation is from Kantaro. Topic is day of week, month, seasonal demand variations, comparing flow estimates across new travel data sources.
Okay, can you see the screen?
Yes.
Okay, thank you for the introduction. My name is Kentaro Mori, and I'm a second-year PhD student at UT Austin, advised by Dr. Kara Gockelman. So travel demand models typically only forecast for a single typical weekday, but in reality, travel demand varies substantially from day to day across the year. Therefore, our next step in advancing travel demand modeling should be to reflect these demand variations into our transportation investment and policy decisions. To this end, we aim to compare two distinct travel data sources that illuminate travel demand variations. Now, what are some data sources that allow us to look at variations in travel demand throughout the year? We have the National Household Travel Survey, but this is for the entire nation and often not ideal for applying it to a regional travel demand model. We have many ways to count traffic on the roads with stationary technology, most common of which is the permanent traffic recorder. which uses loop detectors to count and sometimes even classify vehicles that pass over it. And this loop detector is shown on the left side. In recent years, there's been some installations of permanent radar traffic counters, which are these side-fire devices, and they use radar technology to obtain a higher resolution traffic counts. There are also loop detectors and cameras utilized at signalized intersections for timing signals, and these can also be applied to record traffic counts. Finally, there's Bluetooth traffic monitoring, which connects to Bluetooth devices, so passing vehicles. And the main advantage of this is that the vehicles can be identified from station to station, so you can calculate the speed of a single vehicle and such. There's also big data solutions, which rely primarily on location-based services, which are from cell phone applications, and also connect the vehicle on onboard GPS technologies. And there are many big data vendors. For example, INRIX and Redis, they offer many products that use these pro vehicle big data to offer things like trip tables, corridor speed bins, and even the trajectory of a single vehicle. And Streetlight is another provider, sorry, it's misspelled here, that provides similar products, but using machine learning to offer things like annual average traffic counts and stuff. This study, we focus on the permanent traffic recorder counts and INRIX Redis trip table counts. The reason we chose permanent traffic recorders is because the data is widely available in most states, and the reason we chose INRIX Redis is Redis offers an easy way to download trip tables for a large area. And one disadvantage with Streetlight is that their machine learning models are trained using permanent traffic recorder counts. So we wanted to separate the two. So first, we'll briefly discuss the permanent traffic recorder counts in Texas. So Texas maintains nearly 400 BTR stations that record traffic counts using loop detectors, as I previously mentioned. And 230 of these are able to classify vehicles into the 13 Federal Highway Administration categories. So you can focus on a specific vehicle type. In this study, we focus only on light-duty passenger vehicles. So even though TxDOT tries to spread them out throughout the state of Texas, the sites are limited and heavily biased towards major roads and highways. They are prone to being offline and not working. And finally, demand cannot exceed, it cannot measure the demand that exceeds the capacity of the roads and spill over to minor roads. So 52 of these 203 vehicle class stations offered counts for over 90% of the days in the 4-year period of 2019 to 2022. And this plot shows the daily total count at these stations. You can see that the year-to-year daily counts align pretty well with the peaks being on Fridays, except for extraordinary events like the COVID-19 pandemic shown in the orange line. It is 2020. And also some major storms that occurred in February of 2021 and 2022. Next, I'll give more information about the INRIX / RIDIS flow estimates. So the regional integrated transport, so RIDIS stands for Regional Integrated Transportation Information System. It's a product, well, it's a platform provided by the University of Maryland to easily access pro vehicle data and analytics. And again, these come from two INRIX data sets, location-based services from cell phone apps and connected vehicle data from in-vehicle GPS systems. And TxDOT purchased this data for 3 spring and 3 fall months of 2021 and 2022, offering 357 days of pro vehicle trip tables. So in theory, such big data should be able to outperform traditional sources in sensing day-to-day demand variations because they are not restricted in the geography that they cover. Thanks to such big data options, many states have actually stopped doing household travel surveys, which is a controversial topic in and of itself. It's not to say that there are not disadvantages. So first, the sampling rate is unknown and unstable. And also, there are too many short distance trips that are erroneously recorded into the database because of how these trip starts and ends are defined. For example, for the connected vehicle data, any engine on, engine off instance is considered a trip. And so this figure shows the daily vehicle kilometers traveled, which is estimated using the INRIX's trip table and the shortest paths obtained on TxDOT's stable analysis model network. You can see that unlike the permanent traffic recorder count data, the demands here are very inconsistent with relatively irregular oscillations. So in order to compare how demand variations are captured in these two data sets, use log linear ordinary least squares regression. So for the BTR data set, the Y variable was the light duty vehicle traffic counts at the PTR stations, at individual PTR stations. And for the INRIX RIDIS data set, the Y was the total daily VKT across the state. So the marginal, what's special about this specification is that the marginal effects are expressed as the ratio changes. So they allow for the comparisons of the coefficients between, even though the Y are different in the two data sets. So the PTR regression used all data from 2013 to 2022 for the 203 stations that record vehicle class types. And we use fixed effects at each PTR station to reflect the station-specific levels of demand and observe heterogeneity. So here is a regression result for the permanent traffic recorder data set. It is quite large. I'll try to walk you through it. So the first set of variables, you will see the day of the week, with Monday being the base. The most notable increase occurs on Friday, where traffic counts increase by 23% of the base Monday value. And also the Saturday counts are second highest at around 9% higher than Mondays. And next, you'll see the month of the year variables with January as a base month. So January is the quietest month of the year, and the summer month of June and July are the busiest with 13 to 14% increase above January's. And next we'll see the year variables, and here you can see that the traffic counts increased year to year, except for 2020 when the pandemic hit. But this improved by the year 2022. We also looked at some key holidays that are known to be busy travel times in the US, and we saw that Tuesday and the Wednesday before Thanksgiving are the most different from the norm, and they see a 30 to 60% increase compared to other Tuesdays and Wednesdays in November. And also Sunday after Thanksgiving is busy as well as a day, December 23rd. Yeah, so just to recap what we just found, so LDV counts vary by 28% across the week on average, falling 4% on Tuesdays relative to Monday, and jumping 23.2% on Fridays, also relative to Monday. January was the least busy, while June and July were the busiest months, with counts 14% more than January. And if you want to avoid traffic, you are gonna not drive on Fridays and Saturdays in June and July, and the 2 days leading up to Thanksgiving, and also the Sunday after, and December 23rd. And here is the regression result for the vehicle PKT estimated from the INRIX or Redis trip table. So we see that the regression table is much smaller here, and this is because no months of year effects or holidays were able to be estimated. But however, we do see some day of the week variations, which are mostly consistent with BTR count results, I would say, with counts being relatively steady from Sunday through Thursday, jumping up on Friday as well as Saturday. However, this increase on Saturday is much bigger than what we observed in the BTR data set. So we see a 17% jump here, whereas it was just 9% in the PTR data. But the Friday increase is similar at 20 versus 23%. And we think that this difference in the Saturday effect is maybe due to the mobile devices being overcounted in a single vehicle, because we know that vehicle occupancy is higher on Saturdays, and it could also be due to a permanent traffic recorder's highway site bias. So in conclusion, significant day-of-week differences are clear in both data sets. However, INRIX data was unable to extract any month-of-year variations due to the large uncorrected shifts in sampling rates. So in order to make better use of big data sets like INRIX's, we need the daily trip or vehicle sampling rates. INRIX is working to provide these sampling rates and also improve the quality of LBS data to prevent the double counting issue. So yeah, thank you for listening. Just let me know if you have any questions, comments, or suggestions. This paper was recently published in Transport Findings, and you can find it at findingspress.org or at the website of Professor Kalkoman. Thank you.
Thank you, Noro. Any questions from the audience? Okay. Yeah, I think I have a very quick question. This is for Texas, right? Only the
Yes.
Texas region. Yeah. I'm just curious because so the seasonal impacts also like comes different for different areas, like the states in the
Right.
north maybe different from the south. I don't know if is it possible that to add any land use, even for the cities in Texas, the variations can be different, like for urban area versus the rural area. Is it like, I think all the 300 points, you put them together to do the regression, right? Is it possible to do separate of them, like to see?
So for the PTR regressions or site by site, we didn't add up the counts across the sites. So because you're using fixed effect, but for the INRIX Redis data set, we summed up all the VKT from the trip table, because it's just not possible to estimate by OD pair. But
Okay.
yeah, I agree. It would be very interesting to add spatial attributes. Yeah, that would definitely be a next step in taking this further.
Yeah.
Thank you.
Cool. And also a question in the chat, like, did you try to consider correlation between the station during the regression? Kind of similar question. Yeah.
No, actually, I just use fixed effects. But yeah, nearby stations are definitely correlated. So yeah, that's a good idea. Thank you.
Cool. Thanks, Naro. Yeah, we have one more presentation. Yeah, sorry, we are like kind of 10 minutes behind schedule, but yeah, let's just quickly start the presentation. It is from Alisa, if I pronounced correctly. The presentation is traffic signal control optimization using genetic algorithm and Vissim simulation.
Okay. Hello, good afternoon, everyone. I'm Isa Rahman from Bangladesh University of Engineering Technology. I'm a recent graduate student, and I'm delighted to present our paper in BTR 6 conference titled Traffic Signal Control Optimization using Vissim and genetic algorithm. So the co-author for this paper is Mohammad Atai Rabbi. He is also a recent graduate, and Dr. Mohammad Niyaz Morshed, who is an associate professor in Bangladesh University of Engineering Technology. Before starting today's presentation, I just like to take 1 minute of your time to discuss some really important things that are happening in our country. So those who don't know what's happening in Bangladesh right now, well, for the last 20 days, it's been a huge and critical condition happening in Bangladesh. A student protest against the government is happening, and for this, around 500 plus students, not people, just students, have been died. And lastly, the protest was for quota system, but consequently it led to the fall of the fascist government that was on Bangladesh for the last 15 years. But in this journey, we lost many of our brothers and sisters. We honor their memory and values. The nation will be always indebted to them. Lastly, we got victory. Today we formed new government, and the head, you guys all should know, the Nobel laureate, Professor Yunus. So we dedicate our presentation today to the brothers and sisters who died in this journey. So let's begin. This is the outline of today's presentation. We start this. So traffic congestion. Traffic congestion is one of the major problems worldwide, affecting every aspect of demographic development and life. Dhaka city, which is the capital of Bangladesh, it faces one of its most significant challenges due to managing and mitigating the traffic. As we can see in the newspaper, Dhaka city loses 3.2 million working hours for traffic congestion daily, and the New York Times reports that Bangladeshi traffic jam that never ends. So for this reason, this research seeks to improve the intersection efficiency through enhancing the traffic signal timing, as well as modeling and using genetic algorithm to improve the overall traffic congestion of Dhaka city. So based on that, the necessity could be summarized that there's the study present for signal optimization are mostly for lane-based advanced traffic, like advanced homogeneous traffic, like in countries like US, but there's a little study present for heterogeneous traffic condition like Dhaka city. Secondly, for a developing country like Bangladesh, the improvement by signal optimization is most suitable in terms of infrastructural limitation, as well as it's user-friendly and environmentally sustainable, with microsimulation in our process because it's widely used and one of the most effective ways to predict the traffic behavior and the urban environment, basically. And lastly, genetic algorithm, which is a search heuristic approach that uses high-level mathematical complex mathematical solutions to get the best result. So from this research, we can expect the outcome of a multi-objective optimized traffic signal control, improve traffic flow and reduce congestion at the Gulshan 2 intersection area. It is the study area we use for our study. And lastly, a cost-effective and implementable solution for the traffic signal optimization that can be adapted for other similar intersection like Dhaka city, which is a heterogeneous and non-based condition. So based on necessity and outcome, the objective can be set to a signal, efficient signal control in our study area, an optimal phase equal to the fixed cycle length. For this study, we used a fixed cycle length of 160 seconds. We have to develop the Vissim microsimulation model of our study area. We have to calibrate and validate the model to make it like real life scenario. And lastly, a comprehensive analysis between different optimization model. We'll use different optimization methods to find the best result for our study area. So for the literature review, the modern trend is to develop, we all know that modern trend is to develop the adaptive or actuated traffic signal control system, but it is a massive infrastructure and high level maintenance program is needed to run this, and which is costly. That's why more than 95% of the traffic signal in the US and Canada still uses fixed traffic control. So it's still worthwhile to use fixed time. We're using Vissim in our study because Patel in his 2070 study compared around 17 traffic simulation model and considered Vissim to be one of the best to simulate the high level detail and flexibility in various traffic scenario. And for it, it'll use genetic algorithm as it's used in, it is also used in various traffic transportation problem. So as it can handle a complex multi-objective problem and find the optimal solution. So why this study area? Gulshan 2 is selected for the study area because as the capital of Dhaka, it serves as one of the main business district, and unlike most of the traffic signal of Dhaka city, it is traffic light control intersection. The authorities are trying to use adaptive signal, but it fails during the peak hour because there's a huge traffic and the flow goes above the saturation. So they used fixed signal time control based on the historical data and experience that how should the cycle be controlled. Lastly, thirdly, the study area is used as there is an absence of non-motorized vehicle like rickshaw. For all those people who don't know, rickshaw is a three-wheeler non-motorized vehicle, kind of like bicycle. So its absence, so this study can be done appropriately using microsimulation model. So we now discuss about the study area characteristics. We can say the intersection is a four-legged intersection with left connector, so the vehicles don't need to go through the intersection to turn left. There is absence of the width of the link is not consistent throughout, and there is also absence of lane discipline. So we consider the whole link to one lane in all sections, and the results are quite similar. For the signal, it's a four-phase signal. Now, for the current scenario, it's a four-phase signal and two signal timing plans present from 9 p.m. and 8 a.m. It's adaptive as the vehicle flow is very less in that time, but on the 8 a.m. to 9 p.m. the vehicle flow is kind of near saturation. So the current practice is using 290 seconds of signal timing, which we are trying to optimize. For the data collection, the authority has connected, and the authority is trying to establish the adaptive traffic signal control, and they have partnered with Chinese technology company Dahua Technology and installed cameras. We collected the footage from all 4 cameras and used it in our model. For the road geometry, the values are collected from GIS map as well as from manually. Vehicle routes are calculated to implement in the model, as well as the vehicle composition. So the Vissim model is developed in several distinct phases to get the desired outcome. Firstly, the transportation infrastructure along with traffic management and signal control are defined in our model to run the simulation efficiently and effectively. The Gulshan to our study area intersection modeling start with the creation of the network model in PTV Vissim 2024. Then out of several 3D models, we selected the only model that is in the current use of Bangladesh. As you can see, it's a 3-wheeler motorized vehicle. For those who know, it's a common vehicle in Bangladesh. We call it CNG. In India, it's called auto rickshaw. Okay, so next up, the model development. We define the route, vehicle path routing. We define the reduced speed area and also the conflict area developed as there is many vehicle flow line intersects with each other. We implemented the 290-second, which is currently in practice, into the V6 signal controller and obtained the results of the current practice scenario. Okay, so calibration. Then we have to calibrate the model to get the ultimate result. Calibration is the process by which individual component of the simulation models are redefined and adjusted. In the microsimulation model, calibration are basically done in 2 phases: system calibration and operational calibration. In the system calibration, in our Vissim model, the vehicle 3D model and their distribution of kinetic parameters are adjusted based on several studies. For each vehicle type, we define the maximum acceleration and desired maximum acceleration, deceleration, desired acceleration, deceleration, and so it's appropriate to our condition. For the operational calibration, 3 sets of parameter, mainly lane changing, lateral, and car following parameters are used. And it was based on several literature study and also numerous iteration to match the current condition as closely as possible. For the car following model, we used Weidman 19.9 parameters, and here's the list of all the calibrated values we used against the default value, which is used in most places in the world. So here is a little demo of our Vissim simulation run, and as you can see here, we can from this model we can get different form of result for like throughput, delay, queue length, and etc. So optimization, here comes the optimization. We optimize the signal time based on 3 methods to compare the result. So firstly, Webster method, Vissim's own optimization method, and by using genetic algorithm. These optimization methods give output result in terms of phase times, set of phase times. Then we use the phase time in the Vissim intersection model and get the necessary result. That is a multi-objective. We are only using the throughput and delay in cases. And we compare the result of the all 3 optimization method and find the best solution. So firstly, the Webster method. According to Webster formula, phase time depends on the saturation flow, which in turn depends on the width of the approaches. So based on Webster formula, a set of phase time is generated for a fixed cycle length, and we used this phase time in our VSIC formula and obtained the necessary results. But in Vissim's own optimization, it works a bit differently. Vissim runs numerous iterations for the current stage-based signal controller until it finds its own optimization signal timing for the intersection model and allocates the phase time accordingly. Here is the Vissim's optimized signal controller and its phase time. And lastly, genetic algorithm. As mentioned earlier, it's a search heuristic approach with find the optima based on high-level computing. The criteria for selecting genetic algorithm is basically its computational feasibility, because it takes less time to get the highest optimal result, LT selection, crossover, mutation, etc. For the limit bound of this study, we're using a cycle length of 160 seconds, and the phase time is also in range. And for the GA code, the value, the code specification values are as follows. For the object function, we have to define an object function in our GA code. We create an object function of the GA code from a simulation RUM, earlier simulation RUM of 220 simulation for different phase times and different scenarios of the traffic. To obtain the traffic characteristics pattern, we use the Python regression class to obtain the throughput and delay pattern so that we can use it to predict the nature of the traffic and use it for optimization. And in case of the fitness code is used to measure the effectiveness of each phase timing. So this fitness function is used in our actual GA code. So to summarize and describe the whole GA process, it goes around initialization, where we start the program with a random set of phase times, but within the range. We decode each phase time according to code specification, and we calculate the fitness so that we can rank the result. From the ranked result, we select the top 20 population to go to the next generation, and on the next generation they cross over. They're the parents, the 20 results, they cross over among each other and create new offsprings that are superior than the previous generation. And lastly, in the mutation stage, the offspring change for some bit so that there is generational variety among themselves. So the total workflow of GA program is as follows. It is iterated by a predefined number so that we can find the optimal green time. So for the result analysis, we analyze the performance of each optimization method's result with the characteristics of the intersection. Here we can see for the vehicle throughput, GA performs relatively better than other optimization method, even though in some cases one optimization can in one link can give better results, but overall the GA performance is better, as well as in the average delay GA results the least in the whole intersection with the 4 links. So to summarize an overview of all the methods for the same fixed signal cycle length, we can see that different methods provide different phase times for each links, and thus it can create a huge significant difference in the total throughput as well as the delay. So in comparison with the real traffic flow, which is happening right now without the optimized flow, we can see that GA performs better with a 10.46% traffic vehicle throughput improvement, around 316 vehicle per hour improvement than the current situation. The GA, in case of delay minimization, GA performs 28.77% better than Webster formula and 24.66% better than the Vissim solution itself. So we can see the genetic algorithm yields the highest traffic performance result among the other methods of Webster and Vissim's own algorithm. So lastly, we can say our model and analysis are limited, as the analysis done for this study was only for a fixed cycle length of 160 seconds. We only considered throughput and delay, but other parameters can also be considered. For example, like effective queue length was not considered. Also, our VC model was, we tried as much as possible to replicate the real scenario, but it's very hard to replicate the Dhaka's heterogeneous traffic condition fully in our model. And lastly, there is limited study on the traffic optimization method for heterogeneous traffic and the driving behavior of Bangladesh, it can be considered a limitation for our research. And lastly, for the recommendation of our study, or we can say the future scope, can be the improve the genetic algorithm and addition of more objectives, multi-objectives will be more parameters to perform it efficiently and adapt optimization model for different study areas. we have to incorporate multiple intersection and different cycle length and create a whole complex network with real life constraint in our model. Conduct a sensitive analysis and find the models that has most influence so that we can optimize them. And lastly, to develop an advanced simulation model for the local condition of Bangladesh, which is heterogeneous traffic flow. These are some of the reference used in our study. This was all from us. Thank you all very much.
Thanks for the presentation, Lisa.
Thank you.
There's a there is a question in the chat. So, is the intersection you are modeling an isolated intersection? Because it may be necessary to include near intersections to get a more reliable simulation that allow accounting for assignation in the network.
Yep. Yes, it's a very good question. Thank you. So, as an isolated intersection, yes, it is an isolated intersection, but it's a very long intersection. So, I would say it's an isolated intersection. But we are trying to incorporate other, as we can see, is the limitation. We are trying to incorporate other intersection nearby it and create a whole network so that the performance could be analyzed better and more accurately. As I again said that there's a little study present for the heterogeneous conditions, so we're mainly focusing on the heterogeneity and also the non